Hi everyone. What I'm doing today is a special bonus lesson to go over the bonding and molecular geometry assignment. Many of us had difficulty on that assignment, so I just wanted to run through exactly what I was looking for, and I'm going to go over each individual question. So if you are looking for a specific one, please, you can skip ahead to that. But if you listen to everything, it's going to give you some valuable pointers that might help you as you go forward. Remember, we are going to be taking our exam on this soon, so this is a special kind of bonus lesson that's really going to help you on that exam. Okay, so what we're going to do is we are going to look at our bonding and molecular geometry assignment here. And what I'm going to do is I'm going to walk you through this example problem and each of the 5 problems that come after this. And let's take a look at our first one here. So when you're doing these problems, the very first thing that you need to do is to count up the number of valence electrons. So in this case, we have 8 valence electrons. So I'm just going to pop that 8 in right there. And then we're going to make our Lewis structure. And when we make our Lewis structure, it says Lewis structure with formal charge on your paper. I'm asking you to forget about the formal charge part. So we're not going to do that for CCP. So here's what we're going to do. We're going to take our atoms, we're going to move them over here. And what I would like you to do is to put the oxygen atom in the center. So one of the things that you'll notice is that I'm sure some of you get frustrated moving these things around. You can also see that I too get frustrated moving them around because sometimes it selects something that's different than what I'm trying to get, but still pretty cool. So let's take a pair of electrons and move these in between the oxygen and hydrogen atoms. So that basically is forming our first bond there. So there's a bond now between hydrogen and oxygen. Hydrogen cannot support more than 2 electrons. So the most you will ever have for for hydrogen is 2 electrons. Once you make those 2 bonds, what I would like you to do is to place the remaining 2 pairs of electrons above and below the oxygen atom. And basically what is going on there is hydrogen can't have more than 2. So any extra that you have to be put on the central atom. And they should be put up in pairs. In fact, when we're doing this today, all of the electrons should be traveling in 2s. You should never have a single electron by itself. They should always be in pairs. All right, the next part of this is identifying, so I'm going to save this really quick, but we're going to come back to it. The next part of this is identifying the number of electron domains and bonding domains. So in order to do this, I'm going to go back to the picture here. You don't have to do what I'm about to show you, but what I wanted to do was show you where these electron domains and bonding domains are located. So in this case, I'm going to use this little circle that I created here to identify, first of all, our bonding or electron domains, and then which ones of those are bonding domains. So let me make a couple of copies of that. Okay, so first one, electron domain number 1, electron domain number 2, electron domain number 3, electron domain number 4. So there are 4 electron domains. Now you'll notice only 2 out of the 4 are sharing electrons with an atom. 2 of them are unshared, but the one on the left, which I'm going to make just a different color to make it stand out here, and the one on the right, those are bonding domains. Bonding domains are when you have an electron domain and you have atoms on both sides of it. So out of our 4 electron domains, 2 of them are bonding domains. So now the nice part is the rest of this assignment, there's resources that we can kind of fall back on. So for the next part, what I'm asking you to do is to go back to your Vesper theory guide. We have all of these different pictures that we created. And what we're looking for is the one that has 4 electron domains, so a 4 in column number 1, and then a 2 in column number 2. So there's 4, 4, 4, 3, 4, 2. Perfect. Okay, so the EDG at the top of the next column stands for electron domain geometry. So in this case, we have a tetrahedral electron domain geometry. So in that part up here where it says electron domain geometry name, we can copy and paste the word tetrahedral. And for the second part, we can copy and paste the word bent. Went to the wrong window there for a second. So there's the word bent. And now this picture that we're going to make, we're going to model off of this one right here. But the only difference is instead of having A's and B's, we're going to have O's and H's. So what you can do, look at where the A is. That's going to be our oxygen in the center. And then the B's are going to be our hydrogens. So I'm going to take this picture here. We're going to grab the oxygen to start off with. We're going to put that in the center. Notice that the lines that I've created for you are already at the correct angles, so you don't have to swing those around or anything. So we're going to put one going up, one going down and to the right, or excuse me, left. So the one going up is going to have a pair of electrons. The one going down and to the left is going to have a pair of electrons. Now these bonds are also already at the correct angle, so you could just move these into position. And then we're going to put our hydrogens on the end of each of these. So we'll put a hydrogen there, and then we'll put another hydrogen here. And then finally, we're left with these arrows. Now, my recommendation, the first thing that you should try and do is make the boxes for these arrows smaller because they're way too big to begin with. Once you do that, you can angle the arrow whichever way you would like it to go, but you want it to end up along the bond. So here's the bond between hydrogen and oxygen, and you want the arrow to point toward the more electronegative atom. So in this case, the more electronegative atom is oxygen. So we're going to have that point toward the oxygen. And then this one we are also going to have go along the bond, and again it's going to point in toward the oxygen there, just like that. And once you do that, you're all done with the picture, so we can move that kind of up to the top left there. There's our final picture. Okay, the last part, the bond angle, is the last part that you're going to get from here. So that bond angle is right here. We can copy and paste that into our example here. The number of sigma and pi bonds. Sigma bonds are what we call single bonds, the first bond. And pi bonds only come into playing if we have more than one bond. So we have a double bond or a triple bond. We'll see that later in the video. So in this case, we have two single bonds. So we have two sigma bonds. And we have no pi bonds because we have no double bonds in this whatsoever. The bond polarity, I mentioned this several times, in all of our examples is going to be polar. The only time that you really see nonpolar bond polarity is when you have two of the same atom. So if we had nitrogen connected to another nitrogen, or oxygen connected to another oxygen. For the molecule polarity, what I did was I went and made kind of like a shortcut guide here. So the molecule polarity in this case, we're going to look for our combination of electron domains and bonding domains. So that was 4-2. So we're going to pick out this one right here. I'm just going to change the color of it so it stands out a little bit for us. So we're going to go with that 4-2, which we called bent, right? We called it bent right up here. So we're going to go with that 4-2, and we are going to say that that 4-2 is polar because of this designation right here, polar. Notice that I wrote what it should be for all of the possible combinations. So in this case, we have a 4-2, which we're going to call polar. So I'm going to go back to here. We're going to write in polar. The second part of this, the intermolecular forces of attraction, I also created a little cheat sheet for. So what you're going to do is you're going to look at this slide, and I'll make these available so that way when you take your exam later, you'll be able to use this as well. So if the molecule is polar, we have two choices. So this one right here or this one right here. If the molecule is polar and has a hydrogen attached to N, O, or F, well, that's exactly what we have. We have a hydrogen attached to O. So in our case, we're going to write down all three of these, LDF, dipole, dipole, and hydrogen bonding. So we have LDF, dipole, dipole, and hydrogen bonding. All right, that wraps up our first example. Let's take a look at our second example, or problem number 1. So in this case, again, we're going to start by counting the electrons. So we have 8 electrons here. Now we're going to make our drawing. So our drawing, we're going to put nitrogen in the center. Remember, hydrogen is never going to go in the center. So nitrogen is going to go in the center. We're going to put one of these on the left side, on the right side, and on the bottom or top. It doesn't really matter where you put them, but we should be putting them on top, bottom, left, and right. I know some websites will show you them at angles, but that's not really what a Lewis structure is going to look like. So we're going to put a pair of electrons connecting them. We're going to put a pair of electrons connecting these guys. And then finally, another pair of electrons that are connecting these. And there we go. We have our 3 hydrogens in position. They're each connected to our nitrogen in the center. Now, the last 2 electrons that are here, those 2 are going to go on top of the nitrogen. Remember, hydrogen only needs 2 electrons. So once you make that bond, you never add any more to hydrogen. And remember to keep those electrons always in pairs. So for the next part, what we're going to do is we are going to identify our electron domains and bonding domains. Again, this part you don't have to do, so you don't have to circle it here, but the reason I'm circling it is so that it's easier for us to see. So I made 4 of them. So we have 1 electron domain here, another electron domain here. Rotate this. We have a 3rd electron domain here, and then finally a 4th electron domain right here on the top. So electron domains are areas where we find electrons. Now, this time, just as a reminder, 3 out of the 4 are bonding domains. So these 3 that I'm coloring in blue, these are the bonding domains. 4 electron domains total, 3 of which are bonding. So I'm going to just move this up to the top left here. Perfect. So in the electron domains, we're putting 4. 3 out of the 4 are bonding. Now we're going to go back to our Vesper theory guide. So let's start back at the top here. Now we're going to look for that combination of 4 and 3. So here we have 2 and 2, 3 and 3, 3 and 2, 4 and 4, getting close. 4 and 3, perfect. So in this case, I'm going to grab the name of the geometry. That's going to be tetrahedral. I'm going to put that up at the top. The next part is the molecular geometry name. That's trigonal pyramidal. I'm going to put that in the second box here. And now I'm going to make my drawing look just like this. So A will be our nitrogen atom, and then the 3 B's will be our 3 hydrogens. So I'm going to double click. I'm going to start off by putting our nitrogen in the center. We're going to put our bonds in place here so we know where to put everything. We have 1 going down and to the left, 1 going up. I'm going to put a hydrogen here. It does get easier, I will say, as you do this enough. So we have our 3 hydrogens placed. Next part is our pair of electrons here up at the top. So now my picture here looks just like my picture here. And finally, we're going to position these 3 arrows. So I'm just going to separate them from each other and make their boxes nice and small so that they're easier to move around. Oops, that's what I was trying to do. There we go. All right, so in this case, nitrogen is more electronegative than hydrogen. The closer you are to the top right on the periodic table, I know it's a lot of different things that we're pulling together here. The closer you are to the top right, the more electronegative you are. So we're going to make these arrows go along each of these bonds. So I'm going to just angle them how I need them first. And then I'll move them into position. So they should go parallel to the bond, and they should point toward the more electronegative, in this case, nitrogen. So we're going to move this one right here. We're going to move this one. You can see me struggle too to get this to change to a 4-headed arrow. There we go. And then finally for our last one, we're going to put that right here. So this is what our final picture looks like. Now we're ready to answer the next couple of questions. So the bond angle, again, you can copy and paste that right from the Vesper Theory Guide. So it's 107, and there are 3 of them. There are 3 sigma bonds in this and no double bonds, so there's no pi bonds. Bond polarity, we said, is going to be always polar. The molecule polarity, now we're going to go back to that cheat sheet that I created. 4 and 3, so this time we're going to be using this one right here. I'll make that a different color so it stands out for us. So we have 4 and 3. And then what we want to do next is, someone's printing something, sorry about that. What we want to do next is we're going to put in what our cheat sheet tells us. So in this case, that's polar. So in this spot, we're going to write in polar. And then finally, for the intermolecular forces of attraction, that's on the next page here. And again, I'll make this little bonus lesson slideshow available to you. We have all 3. So we have a molecule that is polar, it has hydrogen, and that hydrogen is attached to a nitrogen. So we have LDF, dipole-dipole, and hydrogen bonding. So that wraps up our first problem. So now we've completed the example problem and the first problem. Okay, let's take a look at our second problem here. This is going to be our first problem that has some double bonds in it. So let's take a look at this. First thing that I want you to do is to count up the number of electrons here. When you do that, you should get an answer of 16. Next thing that we're going to do is we are going to put our atoms in place. Now, you're going to put the less electronegative atom in the center. So in this case, the less electronegative atom is carbon. So that's what's going to go in the center. And these 2 oxygens will go on the outside of the carbon. So our picture is going to look like this. And then just like we were doing earlier, the very first thing that you want to do is connect your central atom to the atoms that are on the outside. So we've done that part. The next thing that I want to do is oxygens. So we have a pair of electrons are going to go around each of our oxygens on all 3 other sides, because there's already one on one side. So we're going to move all of these around our oxygens, just like this. And when we're all done, you'll notice that we have a problem. And then we're going to look at how to fix that problem. So this pair of electrons is going to go on this side. This pair of electrons is going to go on this side. And the problem that we have is that every atom is trying to get up to 8 electrons. That's what completes the octet. And right now, both of our oxygen atoms have 8, but our carbon does not. It only has 4. So what we have to do is we have to take some of these electrons that are on just the oxygen and move them. It's going to be difficult because that oxygen gets in the way there. We're going to move them so that they form our first double bonds. So I'm going to move this oxygen back into place here. Now I'm going to do the same thing over here. If you can grab a single electron and move it, great. If you're unable to do that, then you might have to move the oxygen out of the way and then move it back at the end. All right, so now we have created double bonds. And basically that means 4 electrons are being shared instead of just 2. Next thing is we need to look for our electron domains. So in this case, electron domains, we're only going to have 2 of them. Oops, hit the wrong thing there. We're only going to have 2 electron domains in this case. So I'll show you where those 2 are. So there's one here, and there's one here. We only figure out electron domains for the central atom. So after we've figured out those 2, and they're both bonding, by the way, so I'll make them both blue. We have 2 electron domains, both of which are bonding. So in this box, we're going to write 2 and 2. Then we're going to go back to our Vesper theory chart. This time we're going to start back at 2 and 2, and look at that, we found it on the first shot. So our molecular geometry is going to be linear, and our electron domain geometry is going to be linear. So we're going to go here, electron domain geometry, linear, molecular geometry, linear. Now we're going to make our picture look like the one in the example. So we're going to put a carbon in the center. Then we're going to put an oxygen on one side, an oxygen on the other side. Move these arrows out of the way here. And now this time, because we have 4 shared electrons, we actually have a double bond. So this is the first case where we have a double bond. So we're going to take this double bond and we are going to move it so that it is in between the 2 arrows. So just so you know, I'm just adjusting this so that it goes in the center. It's a little easier to place. So we're going to have a double bond here. We're going to have a second double bond here. I'm just going to move this oxygen over a little bit. There we go. So we have 2 double bonds, and this time the arrows are actually going to point outward because oxygen is more electronegative than carbon is. So out toward oxygen. And we're going to rotate this one 180. This is also going to point out toward oxygen. And there you go. There's your final picture. So the one thing that I want to remind everyone of is, well, first of all, the bond angle. So we have 180-degree bond angle here. So we could copy and paste that right in. When we're talking about single bonds and double bonds have one of each, 1 sigma and 1 pi. So every bond starts off with a sigma bond. That's why in all of the examples that we've seen previously, we've only talked about sigma bonds. Now that we have a double bond, think of one of the 2 as being a sigma and the other one being a pi. So 1 sigma, if you look over here, 1 sigma and 1 pi, 1 sigma and 1 pi. So we wind up with 2 of each. So a double bond is 1 sigma and 1 pi. Because we have 2 double bonds in this molecule, we have 2 of each. The next one, the bond polarity, we're going to say is polar. The molecule polarity, let's go back to our little cheat sheet here. The molecule polarity for a 2,2, it says is nonpolar. So in this box, this will be our first example where we have a nonpolar. And then over here where it says intermolecular forces of attraction, for a nonpolar, we're going to go with, here's our cheat sheet for that. If the molecule is nonpolar, LDF only. Okay, so in this spot, we're putting LDF and nothing else. So that completes example number 2 on the bonding and molecular geometry homework. Let's look at the third problem. So in the third problem, we have a total of 12 electrons. I'm going to drop that in there. So now, let's see. I'm going to move our hydrogens and our carbons around here. And our oxygen. Notice that I tried to grab the carbon first, and it knew that, and that's why it decided to grab everything else first. Okay, so we're going to move our atoms just a little bit closer. So I'm going to start off by connecting up my 2 hydrogens. So I'm going to connect a hydrogen on the left side. I'm going to connect, let's move that out of the way for a second. I'm going to connect up my hydrogen on the right side. The next thing I'm going to do is connect the oxygen down here. Now, remember, every atom wants to have 8 except for hydrogen. Hydrogen only wants 2. So the hydrogens you're done with. Now we're going to take these electrons that are left and we're going to move them onto the oxygen. So I'm going to move a pair there, move another pair to the other side of oxygen, and then finally I'm going to move this last pair down below. Now I'm doing this on purpose, so hopefully it'll let me move them again. So what I want you to see here is that carbon only has 6 electrons right now. So 2, 4, 6, but it needs 8. So what we need to do is move these electrons into another double bond. So this will be our second example where we have a double bond. So you notice the double bond is right here. Now I'm going to add in my electron domains. So let's see here. We're going to get, oh, I did that again. I meant to do this. So we're going to have one electron domain. That's right here. So a double bond counts as one electron domain. So that's one. Next electron domain that we're going to do, oops. Next electron domain that we're going to do is going to be up here on the top. That's 2. And the third one is going to be right here. And I have an extra circle, which I'm going to get rid of. So we have 3 electron domains. And if you notice, all 3 of them are in between atoms. So all 3 of them are bonding domains. So in our electron domains and bonding domains, we're going to put a 3 and then another 3. Okay, so let's go back to our list here. So we have 2 and 2. No. Ah, perfect. We have 3 and 3. So trigonal planar and trigonal planar. So we can copy and paste that into both spots, here and here. Now we're going to make our picture, and our picture should look like this. Almost looks like kind of like a triangle. So we're going to have our carbon in the center, and then 2 of the hydrogens, and then an oxygen. So let's see here. So we're going to have our carbon in the center here. And we're going to have, let's see, what is it letting me grab here? I'm going to move our oxygen into one of these spots. I'll put it on top. And then our hydrogens in the other spots. Now, this time you will need to just tweak these just a little bit. So we're going to have down and to the left. And down and to the right. So that's going to be where my 2 hydrogens are. And then my oxygen, which is at the top, that's going to be connected with this double bond. So I'm going to move this. Let's make it in the center there. There we go. Flip this so that it's nice and straight up. And we're going to put that right there. Okay, so that's what our picture looks like. Now we just have to place these arrows. So we're going to place the arrows. Remember, the arrows are going to point toward the more electronegative elements. So oxygen out of all of these is the most electronegative. So we're going to have an arrow pointing up toward oxygen. Like this. Then for our other 2, we're going to have arrows pointing in toward the carbon. So we're going to have one on the left side here. It lets me move it. There we go. In toward carbon. And then on the right side as well, in toward the carbon, which is the more electronegative one, the closer to the top right on the periodic table. Now, this is where it gets a little tricky. So the cheat sheet that I made for you says that a 3-3 should be nonpolar. However, that's only true if everything attached is the same. But because we have 2 hydrogens and 1 oxygen attached, automatically this is going to be polar. So in this case, what we're going to do, I'm a little ahead of myself, for the molecule polarity here, we're going to write in polar. This is also going to be polar as usual. Okay. The number of, well, let's go for the bond angles. That's there. Drop that in. The number of sigma bonds. We have 1 single bond, so that's 1. We have another single bond, so that's 2. And we have a double bond, so that's 3 for the sigma bonds. And then a double bond, remember, is 1 of each, so it also has 1 pi bond. And then finally, for the last part, we have polar. We're going to check our designation here. So if the molecule is polar, LDF and dipole-dipole, does the molecule have a hydrogen attached to NO or F? This is where it gets really tricky. Does it have a hydrogen? Yes. Is it attached to NO or F? The answer is no. So this is just polar. It's not that hydrogen bonding polar. So in this case, we're going to write LDF and dipole, and that's it. Okay, we are almost done. Hang in there, everyone. We're going to approach our fourth example here. I'm getting tired too, I'll let you know. All right, so the next one here, we have sulfur dioxide. So we have a total of 18 electrons. So if you count up all of those, you'll get 18. We're going to put our sulfur in the center. We're going to put oxygens on either side of it. We'll put an oxygen to the right, another oxygen to the left. Then we can start putting in our pairs of electrons. So we're going to put in a pair here. Another pair to connect up my oxygen on the right. Now we're going to go around the outside of each of the oxygens. So 2, 4, 2 here, 4, 2 there. Okay, so now both oxygens have the 8 that they need. I'm left with 2 extra electrons. So those extra electrons are going to go right here in the center on top of sulfur. So now the oxygen that is on the right side has 8. The oxygen on the left side has 8. But the oxygen in the center only has, or excuse me, the sulfur in the center only has 6. So I need to move electrons into a double bond. So I'm just going to pick one of the oxygens, doesn't matter which one you do, move them into the center there. So now we have to figure out electron domains. So for the electron domains part, I'm going to make a circle here. I'm going to make 2 more. So the first thing is we have 1 electron domain here. We have a second electron domain. I'm just going to flatten this out a little bit. We have a second electron domain right here at the top. And we have our third electron domain over here on the left side. So that's right there. Okay. And then of those 3 electron domains, let's look at which ones are bonding. This is a bonding one. This is a bonding one. So 3 total, 2 of which are bonding. So in this box, 3 total, 2 of which are bonding. Now we go to the Vesper theory guide. We're looking for 3, 2. Perfect, we found it. So now we can copy these names. Trigonal planar, that part's up here. And the molecular geometry name is called bent. Again, scientists are not very original, so sometimes we reuse names. So bent again. And just while I'm here, I'm going to grab that bond angle as well. So bond angle here, we're going to drop that in over there. Okay, for the next part, we are going to make our molecular geometry picture look like this picture. So we're going to have a bond up, a bond down and to the right, and then a pair of electrons down and to the left. So, and it doesn't matter where our double bond goes. It's either going to be the one that's up or the one that's down and to the right, but it doesn't matter which one you choose. So we're going to swing this around here. Put that on top. Move this oxygen over to here. This oxygen down here. Swing this so that we get the angle here. Drop that in. Get the angle going the other way for my electrons. Drop that in. And then let's put our electrons right on the end here. Okay, now we have these 2 arrows to deal with. So there's the first one. There's our second one. We want them to go along the bond and point toward the more electronegative atom. So oxygen is the more electronegative atom. So we're going to have them point toward the oxygen atoms. So So we're going to have 1 point straight up. We're going to have 1 point straight down and to the right, just like that. And we're going to move this over, and then we'll just hold on 1 second here. And move this over, and then we're going to save and close that. Not really large. We don't need it to be that big. Okay, so the number of sigma bonds. So we have a single bond here, that's 1. And then we have a double bond, so that's 1 and 1. So we have 2 sigma and 1 pi. So over here we have 2 sigma, we have 1 pi. Then down here for bond polarity, remember that's always going to be polar. The molecule polarity, so we go to our cheat sheet here for a 3-2. It's going to be this one right here. Colors haven't I used yet. Look at this green. So we have a 3-2. That's definitely going to be polar. And then looking at the second part of our cheat sheet here, is the molecule polar? Yes. It doesn't have any hydrogen, so it's not going to be this one down here. So we're going to get LDF and dipole-dipole. Okay, now on to the final problem. I know some of you thought we might never get here. At least that's how I felt. All right, so let's take a look at how the chlorines look. So, or how the number of valence electrons look. So chlorines give us 7, so that's 7 times 3, that's 21. 22 because of the 1 from hydrogen, plus 4 more, so a total of 26. Could have also just counted all these little dots here. So now let's make our picture. Okay, so hydrogen will not go in the center. Instead, the less electronegative carbon will go in the center, and our chlorines will kind of go around it, top, bottom, left, and right for all of these. So there we go, and then we'll go ahead and put our carbon in the center. Okay, first thing I'm going to do, connect up my atoms. So we have 2 here. We have 2 here. We have 2 here. I'm just going to move this chlorine a little closer. And we have 2 more here. Move this chlorine closer. Excellent. So the next part, hydrogen, remember, is satisfied with just 2, so it's not going to get any more. So now I'm going to take the rest of these electrons and we're going to move them so that they surround all of our chlorines with 8. Oops, that's a 3 there. Yeah. I try and grab them 2 at a time, so it just makes moving them a little bit easier and quicker. All right, so my 2 outside chlorines have the 8. I'm going to go for the chlorine on the bottom. Okay, the nice part about this one is we're done. There are no double bonds to speak of here, so now let's go ahead and identify the number of electron domains and bonding domains. So in terms of electron domains, we have 4 of them. So here's one. Here's one. Oops, let me rotate this. Here's one. And then there's one down at the bottom there. And out of the 4 electron domains, all 4 of them are bonding. So I'm going to take all 4 of these and just change them to blue. Again, you don't have to worry about doing this. I'm just doing this to show you which ones are bonding domains and which ones are electron domains. In this case, all 4 are bonding domains. So 4 electron domains total, all 4 are bonding. So we go into our VSEPR theory guide. Let's keep going down. Bam, 4 electron domains, 4 bonding domains. So the name is tetrahedral. So we have tetrahedral in both spots. So tetrahedral here, And while I'm there, I'm going to grab that bond angle of 109.5. There's 6 of those. So we can put that there. Okay. Now, you'll notice that we have no double bonds here, right? So we have 4 sigma bonds, no pi bonds. Let's make our drawing now. So again, carbon is going to go in the center. We're going to have something going up, something down and to the left, something coming out of the plane of the board, and something back behind the plane. And for these, it doesn't matter where we put what. I'm just going to use, I'm going to make it look like our Lewis structure. Oops, I hate when I do that. I'm going to make it look like our Lewis structure. So we're going to put a chlorine in all of these bottom positions, and we'll put the hydrogen at the top. And finally, for all of these arrows, now the arrows are going to point toward the more electronegative atom, like we always say. So in most cases, that's going to be the chlorine. So we're going to make 3 of them point toward chlorines. Let's see if I can grab one of these. So I'm going to make 1 point down and to the left. I'm going to make 1 point kind of down and to the right a little bit. One's going to point a little bit out here. It would let me grab it. There we go. Oops. It doesn't need to be that big. So we're going to point out toward a chlorine. We're going to point down toward a chlorine there. We're going to point down toward a chlorine here. And then lastly, we are going to have this last one, if I can get it to move. This last one is going to point down toward the carbon. So because hydrogen is less electronegative than carbon, this one is actually going to point downward. And there we go. So I'm going to have it point down just like that, in toward the carbon. Now, because we have different things on the outside, they're not all chlorines. Because we have different things, this one's going to be an automatic polar down here for the molecule. This one, of course, is always going to be polar. And then the last thing that we're going to have here, intermolecular forces of attraction. We do have a hydrogen. It is not connected to NO or F. So it is polar, but no hydrogen bonding. So just LDF and dipole-dipole. Okay, so at this point, we have finished the last problem. I know that was a long video. If you actually did take the time to watch this, one of the things that I want to mention to you is that when you take your test on Friday, I'm going to be using examples from this assignment on your test. So you should be able to get 100% on this part because I'm going to use some of these very same examples. So if you took the time to watch this video, you'll learn that little fact. And good luck to you on your test this week. And if you have any other questions, please let me know. All right, have a great week.